This is an example of a problem from Chapter 25. What we have is a device, an exercise device that was advertised on TV. So you've probably seen these things. It could be treadmills or rowing machines or some other kind of fancy thing. And by using it 3 times a week for 20 weeks, no, for 20 minutes, their resting pulse rate beats were measured before and then tested again after 6 weeks. So they use this machine for 6 weeks. Results are in the table. Okay, so they want to know, is there evidence that this kind of exercise can reduce resting pulse rates? And if so, by how much? So clearly they want us to do a test and they want to see a confidence interval. So the first thing I want to do is I want to just sort of go through the conditions. So let's start there. And let's start with some of the easy ones. So first of all, a random sample. So they don't say. So let's just assume the men were chosen randomly. Okay. It's not that important right now to go through this in great detail because there's other conditions that are more important. So the 10% condition, that shouldn't be too hard to justify unless we're on a stranded island, that 10 men is less than 10% of all men. Okay, so I think we're in good shape there. Now let's see, independence. So for the first part of independence is taken care of, that one male's resting pulse rate should be independent of other men. Okay, unless they're doing something very similar, eating the same food, and maybe if they were all on a submarine or something, maybe then there would be some dependencies. But I'm not sure. I think they're independent because pulse rates are pretty much related to a person's sort of chemistry and anatomy. So moving on, the next thing is independent groups. And there we can see that no, they're not independent. Okay, that this group is not independent. These are the same men. So as you can kind of see, here's Franco has a very high resting pulse to start, so it went down, but it's still high. And then you might find somebody else. Here's Alan. His resting pulse sort of stays the same, but it's low to begin with and low after. So there's a dependency. The results, the values depend on the others. So we don't have that. So what that means is that we can't say we can't look at the mean of these values before and then compare them to the mean after. We can't do that. So what we have to do instead is we have to create a difference. Okay, so the difference. And then we can look at, we'll use d bar so we'll take those differences. So what we could do is we could say, I don't know if that's the right notation. We'll just say before minus after, okay, and that's what we'd use to get these differences. All right, so the quick way to do that is to put the data in L1 and L2 and then say L3, and your calculator is equal to L1 minus L2. Alright, so I'll come back to that. So here, instead of saying independent groups, that'd be kind of a mistake in this case. Let me do that again. What we want to say instead is what we have. It's matched pairs data. Okay, we have data collected before and after for the same subjects. Alright, so we're pretty good to go. We need to check the nearly normal condition. So we need to have a histogram of these differences. Okay, so what I'm going to do is I'm going to show you how I did that. I used the calculator. So let me see. Let me just slide this over a little bit. Edit. Copy. Let's see if this will work. Let me see if I can paste this. Yeah, there we go. So let me go through these calculator commands with you. So I started with just putting the data, like I said, into L1 and L2. And then I put my cursor right here in the top and say L3 equals L1 minus L2. And then I get all the differences. So here they are. Okay, so these are my differences. And then I can do a stats plot. And I had to play around for a while. But you can see here's my histogram. I think I started at -2, and my bin size is equal to 3. So it doesn't have to be perfect, but I played around with it just a little bit, and I got something that looks a little bit unimodal and reasonably symmetric for such a small sample size. So just say right here, yes, the distribution of the differences appears to be reasonably unimodal and symmetric. We really don't want to dwell too much on this right now, because the thing we're really trying to, that's new, is how to do this test. Okay, so we get the data into here, all right, and we have our conditions. So we could say the conditions are met. So we will proceed with a matched pairs T test using a student's T model. And so n minus 1, so 10 minus 1, 9 degrees of freedom. All right, so we're ready to do the model, so you kind of do this ahead of time anyway. So here we go to stat, okay, and then we go to test and just pick t-test, and from there we give it L3, okay, and we check with our alternative hypotheses. Oh, we didn't write those. Oh, my bad. So let's talk about this for a minute. I was too quick to show you. I wanted to show you that independence is the key thing you got to check for. So let's just write our hypotheses real quick. So our null hypotheses, what we're going to say is the mean of these differences is equal to 0. What that means is, what we're going to say is the exercise, if the exercise machine doesn't really help lower the pulse rate, then these differences here would be 0. There'd be no change in pulse rate. And certainly the mean would be 0, or very close to 0. So our center for the model would be 0. Okay, and so we would say that the exercise machine or device does not change the mean pulse rate of men, I guess, if they use it for 6 weeks. All right, so the alternative would be that the difference does go down. So if let's make sure we get what we're saying is it goes down, and if we did L1 minus L2, so then we would say that that should be greater than 0. Okay, so what we're saying is that difference is going to be greater than 0. So we would say something the same. The exercise device does result in a mean decrease in pulse rate of men if they use it for 6 weeks. I think if you thought through it, you could write slightly better hypothesis statements than what I just wrote, but I'm trying to go kind of fast here. Okay, so that helps us understand that we want to say greater than. So then when you do calculate, here's the results you get. So we've got our t-value, and we've got our p-value, and in x bar, this is actually d bar for our notation, and in sx is actually the standard deviation. Okay, so what we're talking about is over here, the results of this data are right here. You could do one variable stats, by the way, and get this. That's a simple way of just getting these results quickly. Okay, so now we're good to go. Oh, if you come back to this command and do it one more time, then you get the model. All right, and you can see that t is way out here. So once again, we have a very small p-value. All right, so let's just go through the calculations the way we would have to document them. So the sample size is 10, and d bar is equal to 2.8, and SD equals, let's see, what was it? 2.8, 2.530. So 2.530. Okay, and our degrees of freedom is 9. And so what we need is we need the standard error of d bar. So that's just like remember for a regular one sample test, it's this. So now we just say d bar divided by the square root of n. So that's going to be 2.8 divided by the square root of 10, and that comes out to be 0.800. Okay, so t, we already have it, but we need to document it. So notation-wise, sometimes we use delta to mean difference. Okay, so mathematically speaking, this is what we're doing. We're going to take the difference, the observed difference, and it's a mean in this case, and that was 2.8. We're going to subtract by the hypothesized value of 0 and divide by the standard error, and that's going to give us 3.5. So the p-value is equal to the probability of d bar greater than 2.8, and that's equivalent to the probability of t greater than 3.5, and that's equal to TCDF of 3.5 out to infinity, and we have to add degrees of freedom. Okay, and then that comes out to be 0.0034, so very small. Okay, so with a p-value this small, we reject HO. Make sure you say that and get that out of the way, and then add some context. So there is strong evidence that, let's say, this form of exercise on the device over, what was it, 6 weeks, can reduce the pulse, the mean pulse rate for men. Okay, so now they also asked us to estimate by how much, so that means confidence interval. So if you don't know where to start, think about the general idea that we have an estimate plus or minus a margin of error. Okay, so here our estimate is d bar, the average, plus or minus the critical value with our degrees of freedom is 9, okay, times the standard error of d bar. Okay, so we have this value. This is 2.8 plus or minus, and we have the standard error of d bar. That was 0.800. Okay, so to find t star, let's use, they didn't tell us, so let's just use 95% confidence level. Okay, so that would be inverse t, and we would do 0.025, and we would go to 9. Okay, and that should give us 2.262. So 2.262. Alright, so then also remember that in the textbook, if you go to the back, the table, there's a column of degrees of freedom, and then on the bottom you have your confidence level. So you find 95, so you go up and you can find the t value. Okay, so here we get a confidence interval of negative 4.66 to negative 1.04. No. I'm sorry, other way around. I get a confidence interval of 1.04 to 4.66. That's so here's one way of doing this, a quick way. Let's go back to the calculator commands. You can also do a t-interval on your calculator, and I've done it right here, so let me just paste it and go back to my work, and let's just check my results against. Let me try again. What happened? Sorry about that, but little technical difficulties. Edit. I did paste. I wanted to do copy. Okay, so let's go back to this, and now we want to do paste. Okay, so on the calculator command, you should, so I get something slightly different on the calculator when I did it by hand. So I'm going to go with the calculator commands. I got 0.990 out to 4.60. So 4.6, if we round, it'd be 1. Okay, so I did it by hand the first time, so I'm a little bit off. But the point is that you go back and you can do stat test, okay, and then just select the t interval. Okay, this command, go in, and you've already have everything set up. Hit calculate, bam, there's your confidence interval right there. And you can see you can kind of do a sanity check. All right, so we are 95% confident that 6 weeks of this exercise program with the device can produce a mean difference actually can produce a mean, let's just say instead of difference, let's say a mean decrease in pulse rate of between, let's say, 0.990 to 4.66 beats per minute. That's what a pulse rate is. And maybe we need to say for men, because this was a test of just men. Okay, so sorry for some of the cumbersome things, but I wanted to do this quickly and get it out to you. So you can kind of see, you have to first recognize that it's matched pairs, which isn't so hard right now because that's what you're doing for chapter 25, but on a test you don't know, so you're going to have to figure it out. So one way is to recognize it. The other way is to stumble across it when you do the independence check. And that's what I tried to model first. The next thing is, don't work so hard. Get the calculator to do the bulk of your work. Okay, then finally, make sure that you understand what you're trying to do with the differences and you get organized correctly. And then you do need to document the computations, even though the calculator did most of the work. Document the computations and then make sure you write your conclusion. And same thing with a confidence interval. Document your work and exploit the calculator and then write a conclusion. Most of this is very similar to a single sample test of means. Okay, good luck.